Good day, everyone. For today's topic on biochemistry, we'll be discussing about the basic principles of bioenergetics and metabolism. Before we discuss on the specific metabolic pathways, we need to understand how energy is transferred from one biologic system to the other. So, bioenergetic is the key concept or the key principle in the governing ways of the governing principles of metabolism. So the references for this lecture is from Biochemistry by Campbell and Leninger's Principle of Biochemistry. But I highly suggest you to read the 13.1 part of Leninger's because it provides a very good discussion and very clear discussion on bioenergetics. So please read the part on Leninger, and for the rest of the metabolism, Biochemistry by Campbell will be our main source. So let's first define what is bioenergetics. Bioenergetics is the quantitative study of energy transduction, which deals with changes of one form of energy into other that occurs in living cells and of the nature and functions of the chemical processes underlying these transductions. Now, living organisms, they exist in a dynamic steady state and never at equilibrium with their surrounding. And maintaining the steady state requires the constant investment of energy. When a cell can no longer obtain energy, it dies and begins to decay towards equilibrium with its surrounding. Okay, wait for a while. Now, bioenergetic lies on the concept of thermodynamics, and it's very important for you to understand and remember the laws of thermodynamics. Okay, so the first law of thermodynamics states that any physical or chemical change, the total amount of energy in the universe remains constant. Energy may change form, or it may be transported into one region to another, but it cannot be created or destroyed. So this principle is what we call the principle of the conservation of energy, or the easiest way to remember this, the concept of of the first law of thermodynamics, that energy is is not created nor destroyed. The second law of thermodynamics states that the universe tends towards decreasing disorder. In all natural processes, the entropy of the universe increases. So it tells us that all processes of all nature, whether that's biologic nature, whether it's chemical nature, it tends towards disorder. That is our real nature. That is why it's called a law. So if you would notice that if you place an ice cube in at room temperature, the second law of thermodynamics is the reason why it melts at the room temperature. Okay? Or if you have your hot cup of coffee in the morning, the second law of thermodynamics explains why it loses heat. Okay. So the second law of thermodynamics is very applicable, especially in our daily lives, because second law of thermodynamics explains how machines work, or how we create energy in the form of either electrical energy, mechanical energy, or even biologic energy. So this law of thermodynamics is very vital for us. And and if you would notice also that the world is really, it tends towards disorder. It is our nature of living organisms, or all entities in the world. It will tend to disorder. So for example, let me take a good example about society. We are born as humans. Okay. From the beginning, we are just humans. There are no structure, there's no social structure, no government, no laws. Now, because of that, it will create, if we if it will create chaos if we just let our nature as it is. So that is why we created structures, we created systems, we created organization to make our society become organized, to be less disorder. Because if we just let nature takes its place, it will very be it will be very chaotic, or it will be in disorder. So that is why we invest a lot of energy and effort in making our society to be organized. So that is why we have laws, we have constitutions, we have government, for our society to be less disordered, to be less chaotic. So parang ganun ang analogy ng thermodynamics. So our natural our natural setup talaga as human beings and as biologic systems or biological organisms, we tend to be in disorder. But we need to make sure but we need to make sure that um, to have the less disorder, so that we can live in a peaceful way, or in a less chaotic way. So again, living organisms cannot create energy from nothing, or living organism cannot destroy energy into nothing, and living organism may transform energy from one form to another. In the process of transforming energy, living organisms must increase the entropy of the universe. So it means that living organisms, if we are existing, we are actually contributing to the disorderness of the whole universe. Okay, so every human that is born, or every organism that is created, we are actually increasing the entropy of the whole universe. When you say entropy, it is the disorder. Okay? In order to maintain organization within themselves, living system must be able to extract usable energy from their surroundings and release useless energy such as heat back to their surroundings. So, di ba, I've mentioned that we tend to be in a disorder. But in order to maintain this organization, to prevent this further disorder, our body or our organisms created system to use energy to make less chaotic, to at least maging organized tayo, maging organized and be uh, less chaotic. So that is why we use energy from our surrounding to maintain that organization. So this brings us to the concept that life needs energy. So recall that living organisms are built of complex structures, and these complex structures, what I've previously mentioned, maintains this organization amidst of our nature being chaotic, being in a state of disorder, or leaning towards that disorder. So we need that energy to keep up with that disorder. Okay. And the ultimate source of energy on Earth is sunlight. So this sunlight is converted into a form of energy where plants can use, plants or microorganisms that undergo photosynthesis. So they produce oxygen and organic products, and these oxygen and organic products are used by the heterotrophs as forms of energy. But that form of energy, it ultimately comes from sunlight. Okay, so it is only the plants and the microorganism has the capacity to use sunlight as their energy. So this is a good video on entropy. So I will post this link later so that you'll have a good um, concept or good grasps of bioenergetics and entropy. So as what I've mentioned previously, the laws of thermodynamics explains why our hot cup of coffee or chocolate drink in the morning loses heat if you just let it stay at room temperature. Okay, so it's the second law of thermodynamics that explains that one. And the three thermodynamic quantities that describe energy changes occurring in chemical reaction, we have the Gibbs free energy, we have enthalpy, and entropy. So we'll be discussing each. When you say Gibbs free energy or delta G, this expresses the amount of an energy capable of doing work during a reaction at constant temperature and pressure. So the Gibbs free energy will tell us if a reaction is exergonic or endergonic reaction. Okay. For an exergonic reaction, it occurs when a reaction proceeds with the release of free energy. That is when the system changes so as to possess less free energy, and the free energy change or delta G or the Gibbs free energy is negative. Okay. For an endergonic reaction, the system gains free energy and the delta G is positive. So basically, exergonic reaction, the Gibbs free energy is negative. For an endergonic reaction, the Gibbs free energy is positive. So please remember these concepts. Now, when uh, when in enthalpy or H, it is the heat content of the reacting system. Okay, when you say enthalpy, it is the heat content. So think of enthalpy as heat. So it reflects the number and kinds of chemical bonds in the reactant and products. And we have two types, the exothermic reactions and endothermic reactions. Now, when a chemical reaction releases heat, it is said to be exothermic. Okay, when it releases heat, it is said to be exothermic, and that the delta H or the enthalpy of this reaction has a negative value. Okay, again, so for an exothermic reaction, the enthalpy is negative, and reacting systems that take up heat from their surroundings are endothermic, and they have a positive value of enthalpy. So a negative value of enthalpy is exothermic, while a positive value for enthalpy is endothermic. Entropy, or S, this is a quantitative expression of the randomness or a disorder in a system. Okay, so entropy, it tells us how a system is in disorder or how random a system is. So when the products of a reaction are less and more disordered than the reactants, the reaction is said to proceed in a gain of entropy. So the units for the Gibbs free energy and enthalpy are thus follows. We have joules per mole or calories per mole. Recall that 1 calorie is 4.184 joules. Okay, and the units for entropy is joules per mole times Kelvin, or joules. And a shortcut way of writing it is joules per mole times K. Now, under the conditions existing in biologic system, including constant temperature and pressure, changes in free energy or the Gibbs free energy, the delta G, the enthalpy, which is the delta H, and the entropy and or delta S are related to each other by this equation. So this delta G is the change in Gibbs free energy of the reacting system. The delta H is the change in the enthalpy of the system. T is the absolute temperature. Delta S is the change in entropy of the system. Now, by convention, delta S has a positive sign when entropy increases. Okay, and delta H, as noted here in this equation, um, a negative sign when heat is released by the system to its surroundings. So delta H is negative if it's an exothermic reaction. So either of these conditions, which are typical of energy favorable processes, tend to make the delta G negative. So delta G of a spontaneous reacting system is always negative. So if you have a negative delta G, then it makes a reaction spontaneous. Okay, so this is the summary of what I just said. So if the delta G is negative, the reaction proceeds forward, meaning it is a spontaneous reaction. If the delta G is 0, then the reaction is at equilibrium. If it's positive, it proceeds in reverse. So it is more or less a non-spontaneous reaction if it's a positive delta G. Now we have also terms spontaneity and reversibility. When you say spontaneous reaction, this is a reaction that can occur without added energy and has a negative value of delta G. So if the Gibbs free energy is negative, it is a spontaneous reaction. If the Gibbs free energy has a positive value, it is a non-spontaneous reaction. So if the Gibbs free energy is positive, that reaction will require energy. And in a reversible reaction, when you say reversible reaction, if the free energy change is only 1 kilocalories per mole, around 4 kilojoules per mole in either direction, the reaction is considered freely. Okay, so if the free energy change is only 1, then it is a reversible reaction. When a stress is applied into a system at equilibrium, the system reacts so as to minimize the effect of that stress. Okay, so the concept of spontaneity or spontaneous reaction can be quite confusing for some, but it merely means that a reaction can occur without any energy. Without any energy, that is why it's called spontaneous. Okay, so just for you to easily understand the concept, a spontaneous reaction is just like similar to water that is held behind a dam on the top of the hill. So, for example, if you have a dam, di ba ang dam, you have nagpundok kag water sa on top of the hill. Okay? And that water is being held by a very big wall. Okay? So, this water that is being held on top of the hill has a lot of potential energy to flow downhill. Okay? But it will not go down the hill unless someone will open the dam. Okay? Because water flows only downhill because of gravity, the direction that is the direction. So this means that the the downhill direction of water flow has a negative value of free energy change or delta G. Okay, and pumping water uphill, or if you transfer water from the lower part of the hill to the upper part of the hill, you require energy, right? It's more effortful to bring water from downhill to uphill. So the free energy change is positive for that one. Again, the flow of water from uphill to downhill has a free negative free energy change, while the flow of water from downhill to uphill has a positive free energy change. And that tells us that you require energy if you move water from downhill to uphill. Okay. So this is what I've previously mentioned. So for an exergonic reaction, or if the delta G is negative, the reaction is spontaneous. Okay. So the reaction is spontaneous, meaning it can occur without any energy. If the reaction has a delta G of more than 0, if it's a positive delta G, so the reaction is not spontaneous because you need energy for that reaction to occur. Okay, so this is just another illustration of the exergonic and endergonic reaction. So this also explains why in an exergonic reaction you don't need any energy. Okay, just like a ball on top of the hill, or on top of a slide. So it's easily to roll down a ball from the top to bottom, while it's very difficult for rolling a ball from bottom to top. Okay, so an exergonic reaction again has a free energy of negative, while the endergonic reaction has a free energy of positive, or delta G positive. So entropy in living systems. So the second law of thermodynamics states that the entropy of the universe increases during all chemical and physical processes, but it does not require that the entropy increases that the entropy increase takes place in the reacting system itself. Living organisms preserve their internal order by taking from the surroundings free energy in the form of nutrients or sunlight, and returning to their surrounding an equal amount of energy as heat and entropy. So it tells us, so this slide tells us that living things are unique thermodynamic states. It's not like other physical systems that occur in our nature. So biologic systems, they are unique in terms of thermodynamics. So most classical treatments of thermodynamics deals with closed systems at equilibrium. So for example, in engineering or in physical systems, most of them, especially in machines, they have a closed systems. So in um, a closed system can exchange energy but not matter with its surroundings. So the energy in closed system can be transferred from their surrounding, but not matter. Okay, because living organisms are not, obviously they are not closed systems. Okay, because we take in energy from food, from plants, from animals. So therefore, we are not just closed system. We are open system. We take in matter in the form of food to gain energy. So that makes us an open system. Okay. So because living systems are open systems, they cannot be at equilibrium as long as they are alive. And however, they can achieve a steady state in a stable condition. Okay, so that makes us different from other physical systems, because in closed systems, most of non-living things are in closed systems, meaning energy is only transferred from the system to its surrounding. In open systems such as living organisms, aside from energy, matter is also exchanged from its surrounding in the form of nutrients. The cells require sources of free energy, and cells are isothermal systems. When you say isothermal systems, they function at essentially constant temperature. Okay, and they also function at a constant pressure. Okay, so heat flow is not a source of energy for cells, because heat can do only as it passes to a zone or object at lower temperature. So heat is also not as is not also a source of energy for cells, right? So from your previous knowledge, heat is a form of energy, but heat is not utilized as energy in living systems. Okay, that but instead, the energy that cells that use is what we call free energy, or the Gibbs free energy. And the Gibbs free energy, or delta G, is the most suitable way to measure energy changes in living systems. Okay? And this delta G, or the Gibbs free energy, allows us to predict the direction of chemical reaction, their exact equilibrium position, and the amount of work they can perform at a constant temperature, and pressure. So how do we acquire Gibbs free energy? So we acquire Gibbs free energy from nutrient molecules and also photosynthesis and also from food that we consume. Okay, and photosynthetic cells such as plants, such as bacteria that undergo photosynthesis, they acquire this Gibbs free energy from solar radiation. Okay, so for us humans, for heterotrophs, we get the Gibbs free energy from nutrient molecules, while in plants and some bacteria, they obtain this Gibbs free energy from the solar radiation. But what is common for both heterotrophs and autotrophs is that both kinds of cells transform this free energy into adenosine triphosphate and other energy-rich compounds capable of providing energy for biological work at a constant temperature. So this gives free energy, okay, is capable of transforming into energy in the form of organic compounds such as adenosine triphosphate and other energy-rich compounds, right, that will be discussed later. And this energy will drive the force of metabolism in our body. Okay, you see from sunlight, which provides the free energy for plants, for bacteria. This is transferred to heterotrophs in the form of food. Okay, so that gives free energy is transferred to heterotrophs by food, and this gives free energy that we obtain from the food will be transferred again into organic compounds, which are considered to have which are considered to be energy rich. Okay, so we have also the concept of coupled reaction. So pairs of biochemical reaction that occur these are pairs of biochemical reaction that occur concurrently in which energy released by one reaction is used in the other reaction. So we have mentioned about endergonic and exergonic reaction. So the importance of knowing about the exergonic and endergonic reaction is that they are usually coupled. Okay, the endergonic reaction is coupled by the exergonic reaction. Okay, because in endergonic reaction, where you have a delta G of positive, you have a positive delta G. While exergonic reaction, they have a negative delta G. And in exergonic reaction, usually energy is released. So unit energy that is released in the exergonic reaction will be used by the endergonic reaction, which utilizes energy. Okay, to further understand about that, we have the transfer of free energy into an exergonic to an endergonic reaction via a high energy intermediate compound. So if you have an exergonic reaction, you are producing energy, and that energy will be used by the endergonic reaction to drive its reaction. So what is metabolism? Metabolism is the sum total of all biochemical reactions that takes place in an organism. When you say catabolism, it is the breakdown of nutrients to provide energy, and anabolism is the synthesis from simpler compounds. So as what previously mentioned in the previous slide, anabolism and catabolism is usually coupled. Okay? So in catabolism, you are breaking down nutrients to provide that free energy, the Gibbs free energy to drive the anabolic reaction. Okay, so when we break down nutrients, we are making energy, and that energy in the form of Gibbs free energy will be used by the anabolic processes, okay, to drive the synthesis or the creation of compounds. Okay, so basically catabolism is like it promotes entropy, while anabolism is the one that maintains the organization of our system. So this is the adaptation of this disorderness. It's the anabolism. But in the process of anabolism, you require energy. And that energy is the Gibbs free energy produced in a catabolic process. So catabolism is somewhat it's not synonymous, but it's actually related to exergonic reactions, while anabolic processes are usually endergonic reactions. Okay, so this graph shows the very basic outline or general outline of metabolism. So in the specific case of photosynthetic organisms such as plants and other bacteria, the ultimate energy source is from the sun, okay, which is the ultimate energy source of Earth. Okay, and in this illustration, it tells us about uh, how catabolism is coupled to anabolism, and that catabolism in especially in heterotroph usually involve the macromolecules, as what we have previously described. We have the fats, the carbohydrates, and proteins. So these nutrients undergo catabolism to provide energy for our body. And that energy will be utilized by the anabolic processes or the endergonic processes to provide number one, structure, number two, to provide the necessary materials for machinery for our cells. So next we'll be discussing the role of oxidation and reduction in metabolism. Though redox reactions are very important in metabolism, and the oxidation reduction reactions, these are reactions dealing with electron transfer from a donor to an acceptor. Okay? So when we say oxidation, it refers to the loss of electrons. When you say reduction, this is the gain of electrons. So the helpful mnemonic for this one is oil rig. Oil stands for oxidation, is loss. Reduction, the rig RIG stands for reduction, is gain. Okay, please take note, redox reaction is not about gaining of oxygen or losing of oxygen. It's the gain or loss of electrons. When you say reducing agent, this is a substance that gives up electrons to other substances, while oxidizing agent, this is a substance that accepts electron from other substances. Now, both oxidizing agent and a reducing agent, they are necessary for transfer of for the transfer of electrons or redox reaction to take place. It's not just only one. So both reducing agent and oxidizing agent must be present for electron transport to occur. Okay. So this shows you that um, how carbon in its reduced form from the far left, which is an alkane, become oxidized to become an alcohol, to become an aldehyde, to a carboxylic acid, and eventually carbon dioxide. So the process, so from left to right, it shows you the increasing oxidation of carbon. So each of these oxidation requires the loss of two electrons. So in the process of oxidation from an alkane to carbon dioxide, you're actually losing electrons in the process. So what are coenzymes? Coenzymes, these are non-protein substances that takes part in an enzymatic reaction and is regenerated at the end of the reaction. So two important electron carriers in metabolisms are NAD plus and FAD. So these are commonly called pyridine nucleotides, and they can dissociate from the enzyme after the reaction. In a typical biological oxidation reaction, hydride from an alcohol is transferred to NAD plus, giving NADH. So what is NAD? Okay, so NAD and NADP plus. So this stands for nicotinamide adenine dinucleotide. So this is an electron acceptor in catabolic pathway. Okay, please remember this is an electron acceptor. So basically, it accepts electron. Therefore, this is an oxidizing agent. Okay, NAD plus and NADP plus, these are oxidizing agents. They accept electrons from other substances. So the structure of the nicotinamide adenine dinucleotide, from the name, it says here we have a nicotinamide ring, we have an adenine ring, and also we have we have, and also our phosphate group. Okay, so in nicotinamide adenine dinucleotide, the nicotinamide ring, it is derived from the vitamin niacin. So the niacin is also known as vitamin B3. So it is the nicotinamide portion that accepts the electron. It accepts two electrons and one hydrogen, which is a hydride, in going into a reduced state. So if the nicotinamide accepts an electron, okay, this is what we call um, NADH. Okay, so that is the importance of the nicotinamide portion of NAD. NADP plus or NADPH is similar with NAD plus except for the presence of phosphate. So in NADP plus, the phosphate is present in the sugar backbone of the adenine group. So it is esterified to phosphate instead of a hydroxyl group. Again, this is the basic structure of NAD and NADH. Again, the difference between NAD and NADH is that in NADH, the nicotinamide ring is already in a reduced form, contains two electrons and one hydrogen. So again, the detailed structure of NAD reveals the basis for the positive electrical charge. So why is it positive charge? So the positive sign is due to the nitrogen atom in the nicotinamide component of the structure. So the active portion of NADP plus is the nicotinamide subunit of the molecule. So electron transfer may be summarized as this one. So in NAD and NADP plus, both of them are just the same. The difference is just the it is phosphorylated. The ribose sugar, the sugar portion of NAD is phosphorylated and in NADP plus. So this is the transfer of reaction in NAD and NADH. So from NAD plus, it undergoes the process of reduction. So reduction is the gain of electrons. So it will be converted to NADH. So from NAD to NADH, this is what we call the reduction. The conversion of NADH back to NAD plus is what we call oxidation. So again, oxidation is loss of electrons, while reduction is gain of electrons. For FAD and FADH2, it's quite different from the structure is different. Its its characteristic is also different, but basically they have the same function as that of the NAD. So FAD stands for flavin adenine dinucleotide. This is derived from vitamin riboflavin. Okay, so riboflavin is vitamin B2, and this function as an electron acceptor. So just as similar to NAD. So in FAD, the dimethyl isoalloxazine ring undergoes the reduction or oxidation. Okay, it's not the nicotinamide portion, it's the dimethyl isoalloxazine ring. So now let's move on to adenine phosphates. So this is very important, especially when we deal with metabolic pathways. So you need to understand the structure of adenine phosphate, especially the adenosine triphosphate. So this is the basic structure of adenine phosphate. We have an adenine group, we have a ribose group, and the phosphate group. AMP stands for adenine monophosphate. So these are nucleotides that are present in RNA molecules. For ADP and ATP, or adenine diphosphate and adenine triphosphate, they differ structurally from AMP in the number of phosphate group present. Okay. So again, this picture shows you the comparison of ADP, of ATP, ADP, and AMP. For adenosine monophosphate, it only contains one phosphate group. For adenosine diphosphate, it contains two phosphate group. And adenosine triphosphate, it contains three phosphate groups. Now, the phosphate bonds in the adenine phosphate, okay, it is bound to the ribose group via the phosphoester bond. Okay, this is a phosphoester bond, while the bond between the phosphate groups, okay, the second and third phosphate groups are what we call the phosphoanhydride bonds. Okay, so please remember, the phosphoester bond is the bond between the phosphate and the ribose, while between phosphate groups, so between two phosphate groups is what we call the phosphoanhydride bonds. And if ATP is hydrolyzed, okay, when you say hydrolyzed, so when you add water, the phosphate group will be removed. Okay, the last portion of the phosphate group will be removed, will be converted to adenosine diphosphate, releasing one inorganic phosphate and energy. And ADP, if it's hydrolyzed with water, it will form adenosine monophosphate with one phosphate group forming energy. So both ATP and ADP can provide energy, but the hydrolysis of AMP, or adenosine monophosphate, will not provide any energy. So why is that? Because the phosphoanhydride bonds, which is the bond between the phosphate groups, between two phosphate groups, have a large negative delta G of hydrolysis. So it is only the phosphoanhydride bonds and not the phosphoester bond has a negative or has a large negative delta G. So the phosphoanhydride bonds has the capacity to provide energy. So these phosphoric anhydride bonds are high energy bonds. Now the bond between the phosphate and the ribose group, it is not considered a high energy bond because it has no large negative delta G, unlike that of the phosphoanhydride bonds. So phosphoanhydride linkages are said to be high energy bonds. Okay, but bond energy is not high, just the delta G of hydrolysis. So if you hydrolyze the phosphoanhydride bond, that is the time where high energy or free energy is produced. Okay, so that is what our system needs, the free energy. Okay, for high energy bonds, compounds with high energy bonds are said to have a high group transfer potentials. For example, the inorganic phosphate may be spontaneously cleaved from ATP for transfer to another compound such as hydroxyl group on glucose. So that high energy bonds will drive transfer of energy. Okay, so as what this is just an emphasis that high energy bonds, they provide the free energy. So phosphoanhydride bonds, when they are hydrolyzed, they will release high amounts of Gibbs free energy. So these are some free energies of hydrolysis of selected organophosphate. Okay, please take note that this is hydrolysis. So if you hydrolyze phosphoenol pyruvate, these are the free energies. So if you hydrolyze the carbamoyl phosphate, the free energy is negative 51.4 kilojoules per mole. Creatinine phosphate, if you hydrolyze creatinine phosphate, you have a free energy of negative 43.1. If you hydrolyze acetyl phosphate, you have a free energy of negative 42.2. If you hydrolyze ATP, you have a negative 30.5. So please remember the free energy of ATP because that is the only thing that you should only remember. Because if you are asked in the exam, in calculating the free energies, usually it is the free energies are provided except for ATP. So please remember the Gibbs free energy of ATP. It's negative 30.5 for kilojoules per mole, or negative 7.3 kilocalories. So standard free energy changes are additive. So if we have two sequential chemical reactions, the free energies of these two reactions are additive. Okay, they are additive algebraically. Okay, so in the case of two sequential chemical reaction in this illustration, so we have reaction one. Reaction one has this equation from A to B or B to A. It has a corresponding free energy or delta G. For a reaction 2, this is the reaction from B to C, or it can be revised into C to B. It can be reversed into C to B, and it has also a corresponding delta G. For the total reaction, so the total reaction of A to C, okay, the delta G is the addition of the delta G of reaction 1 and reaction 2. So as the two reactions are sequential, okay, the reactant B cancels out to give the overall reaction A to C, which has its own equilibrium constant and thus its own standard free energy change called the delta G total. So again, this slide just tells you that the delta G values of sequential chemical reactions are additive. Okay, so for you to provide a more uh, for a more um, a clearer picture of these additive properties. So if you have two reactions, two sequential reactions from A to B, it has a corresponding delta G. From B to C, it has a corresponding delta G. And if you add up the entire process or the entire reaction, the delta G of the first reaction and the delta G of the second reaction are just additive. So basically, you just add them. Now, the problem here is that if you know how to add or subtract algebraically, so you have already known that since grade school how to add with negative values, right? Okay. So for example, if you have this reaction, so from reactant A, it can produce B plus C. So this is the reaction 1. For reaction 2, we have B to produce D. So the first reaction has a delta G of 21 kilojoules, while the second reaction from B to D, it has this gives free energy of negative 34 kilojoules. So based on this principle, standard free energy changes are additive in a sequential chemical reaction. Therefore, from A forming C plus D, so B will cancel out. Okay, so B will cancel out. So the delta G for that matter is the sum of positive 21 and the sum of positive 21 and negative 34, which will give you negative 13 kilojoules. Okay, so the one that is enclosed in the parentheses are just the equivalent kilocalories. So that is just a conversion, but they're just the same. The important thing is here is you know whether the delta G is negative or positive. So again, if the total delta G for that sequential reaction is negative, then that reaction is considered spontaneous. While if you have a positive delta G, that reaction will be non-spontaneous. Okay, so let's have a sample calculation. So predict if the reaction below is spontaneous or non-spontaneous. So for this reaction, we have ADP plus phosphoenolpyruvate forming ATP plus pyruvate. Okay, so in this total reaction, there are two separate individual reactions that takes place. So the reaction one is, first is the hydrolysis of phosphoenolpyruvate. So again, in hydrolysis, you add water to cleave that phosphoenolpyruvate to form pyruvate and inorganic phosphate. So that is reaction one. For reaction two, it is the form the formation of ADP to plus inorganic phosphate to form ATP plus water. Okay, so that is reaction 2. So how do we calculate for the total Gibbs free energy of this reaction? So we get so we calculate it by just adding the delta G of reaction 1 and reaction 2. So how do we get the delta G for each reaction? So we base it on the table. So for the first reaction, the hydrolysis of phosphoenolpyruvate. So again, this table shows you the free energy of hydrolysis. Again, the term here is hydrolysis. So phosphoenolpyruvate hydrolysis, it has a free energy of negative 61.9 kilojoules mole, while the hydrolysis of ATP to ADP is negative 30.5. Okay, but take note that the reaction to in this sample for this problem, it's ADP to ATP. Okay, so how do we go about that? So for phosphoenolpyruvate, we just copy the negative 61.9 or negative 14.8, whatever suits you, but you can actually try both. Okay, so for phosphoenolpyruvate, we can use the negative 61.9 kilojoules per mole. So in this reaction, the Gibbs free energy of the hydrolysis of phosphoenolpyruvate to pyruvate has a delta G of negative 61.9 kilojoules per mole. For reaction 2, which is ADP to ATP, it's positive 30.5. So how do we get that positive 30.5? So from this table, hydrolysis of ATP to ADP is negative 30.5. Now, since our reaction is the reverse, which is ADP to ATP, we just need to change the sign of the delta G, which is positive. So for this one, the delta G for reaction 2 is positive 30.5 kilojoules per mole. And to get the total free energy for these reactions, you just need to add algebraically. So the sum of negative 61.9 and 30.5 will give you a negative 31.4 kilojoules per mole. And the important thing here is the sign. So since the sign of the delta G total is negative, okay, so the sign of the delta G total is negative, then the reaction is spontaneous. Okay, so please take note that even if the reaction is spontaneous, okay, so if the reaction is spontaneous, it will not if, just like in laboratory, nothing will happen if you just put it in a test tube. Okay, so the reaction is spontaneous, but with the help of the use of enzymes. So enzymes are needed to catalyze this reaction, and it's not just on its own. So these biologic reactions need enzyme for it to be carried out. Okay, so we'll have more sample calculations for our activities for this one. And this is my last slide. So thank you very much. So please read chapter 15 of Campbell and chapter 13.1 of Leninger for additional information. Okay, so thank you very much and stay safe.